So in this video, I'm going to introduce Gauss's law, which is covered in chapter 25-3 in the textbook. Okay, so Gauss's law, well, Gauss's law relates the electric flux. So remember the integral E dot dA is electric flux, and it relates it to the charge enclosed in the surface over which you're calculating that flux. So first off, just some definitions of constants. So you notice there's this little epsilon naught constant, so that's just a constant of nature. It's known as the permittivity of free space. It has a value of 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And actually it's just an alternative way to write this Coulomb's law constant K that we used back a couple chapters ago. So epsilon naught is exactly the same thing as 1 over 4 pi times Coulomb's law constant K. So we could have just as easily, when we did Coulomb's law, instead of writing our constant as K, we could have written it as 1 over 4 pi epsilon naught. So they're telling you the exact same information, just in slightly different ways. And it just turns out if you use K, then Coulomb's law looks simpler. If you use epsilon naught, then Gauss's law looks simpler. So just some mathematical stuff here. So you notice we've got an integral, and there's an integral with the little circle around it. So the circle in general, when you're doing an integral, it means closed. So here we're doing an area integral since it's dA. So the circle means that we're doing the integral over a closed surface. So, and sort of more generally, Gauss's law is a mathematical relationship between a volume integral over the source of a field, so that's our charge, our Q, inside this closed surface, and the closed surface integral over the value of the field on the surface, so the flux. So it relates the flux over some closed surface to the charge enclosed inside that surface, and that is Gauss's law. Okay, so in practice, it actually looks quite tempting because it looks very simple, and in fact, it is quite simple. Now, of course, the kicker is that actually calculating that flux over some closed surface can actually be pretty hard. So in general, the strategy is, you're going to choose an imaginary closed Gaussian surface over which to calculate the flux. In this step here, that's really the whole trick in Gauss's law, because the whole trick is to pick some surface where calculating that flux is going to be easy. And generally, what you want to do is you want to exploit the symmetry of your charge distribution. Because if your charge distribution has some symmetry, then you can pick your surface to match that symmetry, and then generally calculating the flux becomes easy. So, and we're going to do some examples of this in class. In particular, well, we'll start off with an example that we know the answer to, so the electric field from a point charge, and then you guys are going to get to look at some other examples of charge distributions that have a lot of symmetry.